Alright, it is time to talk about the AOIME. AOIME. No, wait, what? AOIME, that's what it's called. It really rolls off the tongue, you know what I'm saying? Or if you're like a cool kid, you could say the AOIME. But like, I'm not a cool kid, so we're going with the AOIME. Hello everybody, I'm Kara, and today we are going to be going over the AOIME whatever thingamajigger. From what I've heard from a lot of my friends, the test was hecka hard, so don't feel bad if you didn't do that great. It's okay. It was pretty hard. In my personal opinion, like for me, I got a lower score on like this one than the previous one. I got a 9 this time instead of a 10, so it's pretty mediocre, not great. Rip. I made 2 really stupid mistakes on this one. Big sad. One thing that I noticed that was kind of weird is that the first 5 were like relatively easy and then just jumps. It was like crazy hard after that. So anyways, let us just get through as many as we can. I'll probably just go through 1 through 10 because I know how to solve the problems, and I'll probably walk you guys through my thought process during the test so that you guys get a better sense of than just me reading off the solutions. So we'll see how it goes. So basically the first one asks you to find the number of ordered pairs m and n such that m squared n is equal to 20 to the 20. And whenever you see these kind of problems where you have positive integers and an equation, you basically want to prime factorize the big number on the right side. So you know that 20 to the 20 is basically equal to 2 squared times 5, because that's a prime factorization of 20 to the 20. So this is just equal to 2 to the 40 times 5 to the 20. Now, let us say that m is equal to 2, right? Then you know that there's only one possible n. If we like divide the equation by m squared, we basically get that n is equal to 20 to the 20 over m squared. So that's just over 4, and that means that n is equal to 2 to the 38 times 5 to the 20. Okay, so basically from this we can see that for every m, there's one n. But we also have to keep in mind that we want positive integers. So the only way for this to be a positive integer, the only way we can have a positive integer m translate to a positive integer n is if m is a positive integer and it divides this, right? Or specifically, m squared has to divide this. That's because if m squared does not divide this, then n is not going to be a whole number, and then we're doomed. So basically we have that m squared divides 2 to the 40 times 5 to the 20, which is the same thing as saying that m divides 2 to the 20 times 5 to the 10. Because think about it, right? If it divides this, it for sure divides this, and if we square it, we're only doubling the prime factors. And if we have less than 22's and we square that, then that's for sure less than 42's, and so on, same with 5. So basically we have this right here, and you guys know how to count positive integer factors. It's just this plus 1 times this plus 1, so 21 times 11 is equal to 231. Very cool! And because for every m there's only one n, each one of these corresponds to a different ordered pair. Epic! Alright, the next one's pretty fun. I like geometric probability. Very cool stuff. And that is a unit square. No, let's draw this better. So basically you have a unit square. This is 0, 0, that's 1, 1. You get the idea. And then basically you have a point. 5/8, 3, so it's somewhere around there. And you choose a p somewhere in this interior. And basically you want the slope to be greater than 1/2. So if you choose p right here, that's fine, because this is clearly greater than 1/2. If you chose it here, it's fine. But if we chose it here, it's less than 1/2 the slope of this line, so that's not right. So essentially whenever you do geometric probability, what you want to do is you want to draw the line that represents the p's that are on the border. And if p barely works, if the slope between it and the point is 1/2, right? So anything on this line, which has slope 1/2, is going to barely work, right? Because if p is here, then the slope of the line between p and the point is going to be 1/2. But we specifically want it to be greater than 1/2, so we got to do this. Wait, this is not to scale. Wait, it should be like that. There you go. And we know that any point underneath this line is going to have a steeper slope than this line, so that means that any point underneath should work. So this area works. And then let's think about it on the other side. So this extends over here, and we know that any point P above it is going to work. Because then if we draw a line here, it's steeper, right? So then we draw this here, and we know that this area over here works as well. So basically, because the area of the square is 1, we just need to find this area right here, the shaded area, in order to find the probability. So the way I did it in the actual thing is I drew this line over here, and I basically found the sum of these two areas, the area of these two rectangles, and then subtracted these two triangles, because trapezoids are really annoying to deal with. Okay, so how do we find this height? We basically know that this length is 5/8, so that means this height is 5/16, because the slope of the line is 1/2. And this is 3/8, so this got to be 3/16. And then this is 5/8, and this is 3/8. So basically, the area of each rectangle is 15 over 64, so we have 2 of those, and then we had to subtract the area of the triangle. So the first triangle is this times this over 2, because base times height over 2. 25 over, what's 8 times 16? 128 times 2, minus 15, wait no, 9 over 128 times 2. And then if we simplify this. So basically we know this part over here is going to be like negative 34, and then we could cancel out a 2, so that becomes negative 17 over 128. And then if we want to convert this over here to over 128, we got to multiply by 2, and we basically get 60 over 128 minus 17 over 128. And then we just do 43 over 128, and you find the sum of the top and the bottom, and what do you get? That is right. You get 181. What a cool... nope. Bruh. Why am I so big brain? What the heck? Bruh. 171. Very cool. I can add, I swear. I know how to add. Okay, very cool. We know how to add. Let's move on to problem 3. So problem 3 is literally the easiest problem on the test if you know how logs work. It's literally like, you just have to use this one trick, and you're done. So basically the two identities you had to know, and these are really common identities if you've worked with log before, is this is equal to log base a of b. And then the other one you gotta know is that log b to the x is equal to x log b. You literally only need to know those two identities, and then this is like trivial, okay? So let's just apply it real quick. So basically the left side is gonna be log 3 to the 20, and then you could pull the 20 outside, so it's 20 log 3, and then the bottom is gonna be x log 2. And then on the right side you're gonna have 20 log 3 over x plus 3 log 2. And then literally these things just automatically cancel out, and you are left with a linear equation. So you get like 20x plus 60 is equal to 20x. And then if we just subtract, we basically get that x is equal to 3 over 100. Very cool. And that's not our answer because we got to add again. God dang it, I hate adding so much. So your answer is 103. Very cool. And I added correctly this time. Oh my god. Very epic. Let us move on to problem 4. Alright, so basically this one is you start with triangle ABC, which is 0, 0, 0, 12, and 16, 0. Probably should have left more space for this. Actually, yeah, let's leave more space for that. So let's say it looks like that. Okay. And then your A prime, B prime, C prime is your other triangle. So A prime is going to be 24, which is like somewhere around here. And then 18, which is like around there. So that's your A prime. Wait, let's label this. And then your B prime is going to be somewhere over here. And then your C prime is going to be somewhere over there. Okay, so literally just looking at this, you can see that your A got rotated here. Your C got rotated there. And your B got rotated there. So just by looking at it, you could probably tell that your point is going to be somewhere over here, and you're rotating 90 degrees clockwise. And it's pretty clear that we're rotating by 90 degrees, right? Because we're taking the horizontal side, the AC, and we're flipping it to here. So A prime, C prime is vertical now. So we know that M is equal to 90 degrees. So M is equal to 90. But then how do we find this point over here? So in the actual test, what I did is like, basically, you know that when you rotate around something, right? Like this distance over here is equal to this distance, right? When you rotate around something, you don't change the distance. You only change the angle it makes with it. So basically, whenever you have equal distances, it's basically the perpendicular bisector. So the perpendicular bisector of all these things intersect at this point. So basically, I found two perpendicular bisectors and found where they intersected. But I'm pretty sure that the better way to do it is just to notice that, like, we already know that it's a 90-degree rotation, right? So you could basically take this line and find the point around which you have to rotate 90 degrees in order to get to the C prime. Okay, this is really not clear. Let me draw it out way bigger. Okay, so let's say you have your point C over here, and you have your point C prime over there. And you know that this distance over here, and this distance over here, so there's 2 and there's 8. So basically, if you have a point here, and you have this is like A over here and B over there, then if you rotate by 90 degrees, you know that this over here has to be B, and this has to be A. Very cool. So essentially we know that b minus a is equal to 2, and we know that a plus b is equal to 8. So we literally just solve this. We get that b is equal to 5 and a is equal to 3. There we go. So essentially we go from 16, 0. We add 5 to the x coordinate to get to here, so that's 21, and we subtract 3, so that's negative 3. Hooray! So now we have x and y, and we add it to m, so we get 90 plus 21 minus 3, and we get, what do we get? 108. Very cool. Epic. Problem 5. Okay, this one was pretty troll as well, but like anyway, so basically you start with the number n, you take the base 4 representation, then sum the digits, and then you base 8 that, and you take the sum of the digits of that, and then you finally get your answer, which is 3 in this case. And basically you want to find the least value of n, such that the base 16 representation can not be expressed using 0 through 9. So essentially that means that the next greatest thing is going to be g of n is equal to 10. Because if you base 16 10, the only way you can represent it is with a. You can't represent it with 0 through 9. So basically what we want to do is we want to reverse engineer this n so that its g of n is equal to 10. So why don't we go back one step, right? So basically we want the sum of the digits of a base 8 representation to equal to 10. So we know that in a base 8 representation, the digits are all between 0 and 7, right? So that means if we want to minimize the number we get, we want to make the last digit as big as possible, so that's going to be 7, and then the next digit has to be 3 in order to sum to 10. So this number right here is the smallest base 8 number whose digits sum to 10. Okay, and if we convert this to base 10, you basically get 3 times 8 plus 7 is equal to 31. So essentially what this says is that 31 is the smallest base 10 number whose base 8 representations digit sum is equal to 10. And remember, we want the smallest of everything, because if we get the smallest of everything, then our n is going to end up being the smallest. Okay, so now basically, we know that this number right here, like the thing that you convert to base 8, is supposed to be the digit sum of a base 4 number. So now we had to find the smallest base 4 number whose sum of the digits is 31. So we could do the exact same strategy. So you basically know that each digit is 0 to 4, right? Right? That's right, okay? You gotta... Nope. I literally thought I was right. What am I doing? Okay, anyways, the point is, it's 0 to 3. Epic. And basically, we want to put the biggest digits at the end so that our number overall is going to be as small as possible. So we want to put a 3, and then another 3, and then another 3, and so on and so forth. And we could put 10 3s. But then there's 1 left over, so we have to add a 1 there. So this right here is the smallest base 4 number whose sum of the digits is 31. So then, if we want to get our n, we literally just convert this to base 10, which we could do using geometric series. So this right here is the 11th digit, right? So that means you do 1 times 4 to the n minus 1, which is 10. And then, for the rest of them, you do 4 to the 9th, plus 4 to the 8th, plus 4 to the 7th, all the way to 1. So you know that it's 4 to the 10, and then if you know how to use geometric series, it's basically going to be a times r to the n minus 1 over r minus 1. So why don't we start with 1, and we'll go up from there. So our a is going to be 3, well, we'll put the 3 outside, and then our a is going to be 1, and then our r is going to be 4, our n is going to be 10, because we go from 9 to 0, so that's 10 things, and then this is going to be 4, so the 3's cancel out, that's good. And then you just get 4 to the 10 times 4, wait, what? Plus 4 to the 10 minus 1. Dude, I almost messed this one up. I literally, okay, so basically you know that 4 to the 10 is basically 2 times 4 to the 10, which is equal to 2 to the 21. I literally read this as 2 to the 20 on the actual test, and I almost got so toasted. That would have been such a sad mistake, it's not even funny. But anyways, then you do a minus 1, and basically you know that 2 to the 10 is 1024, right? So 2 to the 21 is just 2 to the 10 squared times 2. But we only want to find the last 3 digits of it, so we only care about the 24, because 1024 we can just chop off this stuff over here, and then this squared, it gives you 576, and then you multiply this by 2, and you get 152, and then you subtract 1 to get your final answer of 151. Epic! Let's go! We did it. We are too good at this game. Alrighty, problem 6. Now this one stumped me for quite a while on the actual thing. I was so confused because the numbers got nasty so fast. So basically the best way to do this is literally just to find the pattern. Like with the recursion problems, if it's a problem 6, it's for sure find a pattern. If it's like problem 7, problem 8, it's probably just find a harder pattern, honestly. Like usually the recursion problems can be solved just using like pattern recognition. Like honestly, if you try hard enough, you can probably find a pattern. There's sometimes a good way to do it, but like finding the pattern is the most straightforward and you don't waste that much time doing it. So, you know that T1 is equal to 20, T2 is equal to 21. If we try T3, it becomes kind of nasty. So why don't we just do it, leave it in terms of T1 and T2. So this becomes 5T1 plus 1 over 25T2, no, the other way around. 5T2, 25T1. Okay, and then if we put in T4, we basically get that it's 5 times T3, so we can plug this in, and we get 5T2 plus 1 over 5T1 plus 1 over 25T2. So if we want to simplify this, let's try it. We basically get that as 5T2 plus 5T1 plus 1 over 5T1 over 25T2. So if we combine the denominators, we get an epic 125 T1 T2. Epic. So now we can get rid of this stuff because we don't need that anymore, and we could find out what T5 is. So T5 is basically going to be 5 times T4, so it's going to be 5T1 plus 5T2 plus 1 over 25 T1 T2 plus 1 over T3, which is 5T2 plus 1 over 25 T1. So now we get rid of T3 and let us use the space to use even more work. It's kind of nasty, but don't worry. If you know how to algebra, it'll be fine. So basically, if we look at the numerator, it's going to be 25t1 t2 plus 5t1 plus 5t2 plus 1. And this is factorable by Simon's favorite factoring trick. So, how are we going to do that? Basically, this is literally just, if you know how to use Simon's favorite factoring trick, it's just 5t1 plus 1 times 5t2 plus 2. I mean 1, yeah. And then, we basically literally just cancel out this, and then you cancel out this, and you are left with 5t1 plus 1 over t2. Holy moly, whack-a-mole, now this is looking nice. We are not yet back at our originals, but we got something cool. So now let's try to get what T6 is. Oh, whoops, I messed up. Wait, hold up. Let's go back a bit. Oh, whoops, we forgot to multiply with the 25 right here. Like, see, there's 25. So that makes this cancel out. So it's basically what we had, except we had to divide by another 25. So it's 5t1 plus 1 over 25t2. Okay, so now we can do T6 finally. And we get 5 times this thing. So that's just 5t1 plus 1 over 5t2. And then this whole thing plus 1 over 25 times this, which is going to be 5t1 plus 5t2 plus 1 over 5t1t2. So basically, let's erase t4. We basically get that the numerator is 5t1 plus 5t2 plus 1 over 5t2. And guess what it cancels out with? That's right, it cancels out with this, it cancels out with that, and then this cancels out with this and that. And then we are only left with our final answer of t1. So T6 is equal to T1, and guess what T7 is? If you do it out, you get T7 is equal to T2. So basically, T1 is equal to T6, T2 is equal to T7, then T3 is equal to T8, and basically every 5 it repeats. So essentially, T2020 is going to be whatever mod 5, and then we can find it here. So we know that 2020 is 0 mod 5. So that means it has to be the same as T5, right? Because T5 is the same as T10, is the same as T15, is the same as T20, and so on and so forth. So we could literally just solve for this thing over here, and we are Gucci. T20 is equal to 5 times 20 plus 1 over 25 times 21. And then this right here is simply equal to 101 over 525. So your answer is going to be 626. OMG, that is crazy stuff. Dude, this one took me so long on the actual competition, but there's even more longer ones to come, don't worry. Okay, so problem 7, like, originally I didn't see how you're supposed to do it, but then I realized that I was overthinking it. So let's just think about it this way. So you basically got your cones, and you got, like, this thing, and you got another cone going that, oh my god, voice cracks. Dude, this is crazy. Bruh. Holy. I'm literally going through puberty again, it's not even funny. But anyways, originally I was so confused because this shape in the middle is so weird. Like, what the heck? How are you even supposed to think about this? Well, basically, the thing that you gotta notice is that, like, let's draw this line here and this line here. So let us consider a sphere that's, like, right touching all these 4 sides. It's kind of like a cyclic quadrilateral, right? There's, like, a thing here and... Oh, no, not a cyclic quadrilateral. It's like an inscribed circle in a quadrilateral. And, you know, it's not guaranteed to have an inscribed circle, but I could prove it to you. And the way I'm going to do that is, let's pretend that we just, like, let's erase this. And let's say we were only considering this cone out here, right? Like vertical cone. And we basically take something that's centered over here, and we find the circle that's tangent to it. So basically, we know that this is going to have some radius, right? However, these cones are exactly congruent, right? So the radius that is tangent to this cone will also make the same circle tangent to the other cone. So this circle actually does not extend outside the other cone. So we want to draw like a more like accurate 3D picture, right? Basically, like, there's going to be, like, this is the outline of the other cone, and then this is the outline of the vertical cone. And basically, it's perfectly tangent at those points. Now, the reason why it has to be centered at that place is, like, let's say we move it down, right? Then we would have to make it smaller to fit inside this horizontal cone, right? Because then it would extend out this way, right? If we moved it up, then it would extend out this way, and that's not good. If we move it left, then we would have to shrink the radius for it to not extend out this way. And same for right. So it has to be centered at this point right here, the intersection of the axes. So basically to solve this problem, you just have to notice that, like, putting the circle tangent to the vertical cone makes it automatically tangent to the other cone. So essentially we just know that we have to find a circle centered at a height 3 and tangent to the cone. So the way we could do that is using similar triangles. So this is a 5, this is a something, r, and this is a 3 over here. So this right here is going to be root 64 plus 9 is equal to root 73. And then by similar triangles, we know that this over this is equal to this over this. So r over 5 is equal to 3 over root 73, so r is equal to 5 over root 73. And that means that r is equal to 225 over 73. Very cool. And that is not our answer. We gotta add. So we basically get their answer as 298. Epic. Alright, problem 8. Okay, another recursion problem. Basically the way I did it, I literally just looked at the pattern again. So you basically have that f1 of x is equal to x minus 1. So where are your zeros? That's right, x is equal to 1. Then f of 2 is equal to x minus 2, 2 minus 1. And where are your zeros? Basically, the way you could think about it is like you're taking x minus 2 is equal to one of these zeros. Because if x minus 2 is equal to one of your zeros, then it's guaranteed for this whole thing to be a 0 as well. So x minus 2 is equal to any of these zeros here, and in this case it's only 1. So basically, in terms of logic, what the statement says is that, like, x is a distance 1 away from 2. So in this case, x is equal to 1 or 3, because both of those are a distance 1 from 2. Then f of 3 is basically going to have that, in order for f of 3 to have a 0, like x minus 3 has to be a 0 of this function over here. So we know that this is equal to 1 or 3. So basically, if we logic it out, right, this equation right here is saying that x is either a distance of 1 from 3 or it's a distance of 3 from 3. So basically that means we could have 3 minus 1, so that's a distance 1 from 3, which is 2, or the other side, which is 4. Or we can have distance 3 on either side, so that's 0 and 6. Then f of 4 basically says that x minus 4 is equal to 0, 2, 4, or 6. So basically, it's a distance 0, 2, 4, or 6 away from 4. And this is basically every 2's, right? So basically, we could say that the biggest distance away from 4 that we could get is negative 6. So we do 4 minus 6 is negative 2. And then we know that we have every 2. So it's going to be 0, 2, 4, up to the max, which is the maximum distance, which is 4 plus 6, which is 10. So 6, 8, 10. And then for x minus 5, then you basically get that is 5. Maximum distance is 10, so it goes from negative 15, and then every 2. So negative 13, negative 12, 11, dot, 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 all the way up till the maximum, which is, oh, sorry, not 15. It should be 5 minus 10. So negative 5, negative 3, all the way up till positive 15. So it seems that every 2, it switches from odds to evens, and that, like, your x starts at 1, 1, 0, negative, or 0, negative 2, negative 5. Oh no, sorry. It goes from 1, 1, 0, negative 2, negative 5. Okay, and what does the end go? 1, 3, 6, 10, 15. Ooh, 1, 3, 6, 10, 15 sounds like a familiar sequence. What is it? That's right, it is a triangular number. So let's erase all this nonsense. And basically, you know that, like, your triangular numbers are going to be, your n's are basically going to be n times n plus 1 over 2. Now we have to find a formula for your start numbers. So we know that it started at 1, then it became 1, then it became 0, then it became negative 2, and then negative 5. So first, there's the difference of 0. Then there's the difference of 1. Then there's the difference of 2. Then there's the difference of 3. Wait a minute, this seems like triangular numbers again. So essentially, if we want to start from here, it's going to be 1, or, well, this is f of 1, so f of 2. So we could start from here. So we could basically say that your triangular numbers is going to be 1, 3, 6. So your first one is going to be n times n minus 1 over 2. But wait up. No, sorry, it should be n minus 2 times n minus 1. Because that way, you're starting with 1, and then you're progressively subtracting 1 more. So for 2, this is just going to be 0, right? So 1 minus 0 is 1. Epic, that's what we wanted. Then for n equals 3, we get 3 times 2 over 2, and you get 1 minus 1 is equal to 0. Very cool. And you could plug it in and see that it works for the rest. So basically, we're summing from here to here, and we're going every 2's. So basically, in order to find your sum, you multiply the sum of the endpoints times the number of pairs. So the sum of the endpoints is pretty easy. You just add these two, and you get like 1 plus n squared plus n minus n squared plus 3n minus 2 over 2. Yeah, this is just equal to 2n. And then if we want to find how many pairs there are, we can find the number of numbers there are, and that's pretty easy. If we just subtract the n from the beginning, divide by 2, and then add 1. See, what do we get? We basically get n squared plus n minus negative n squared plus 3n minus 2 over 2, and then we got a minus 1 over here because we subtracted it. Okay, and then if we just simplify this, we basically literally just get, what do we get? We basically get just n squared plus n. Very cool. Or no, n squared minus n. And then since we're going every other, we basically had to divide by 2 and then add 1. And now this right here is the number of numbers we're summing. So in order to find the number of pairs, we divide by 2 again. And then we had to multiply by this to find our final sum, so it's n times n squared minus n plus 2 over 2. And we can verify this works. So for f of 1, we could plug it in, and we get 1. Which makes sense, right? Because we said that the sum of the roots for f of 1 was just x equals 1, so that makes sense. Then for 2, it's 2 times 4 minus 2 plus 2, so that's 4. And that makes sense, so we have x equals 1, x equals 3, sum them, you get 4. Alright, so basically we're left with this, n times n squared minus n plus 2 over 2. And this has to be greater than or equal to 500,000. And now, if we multiply the 2 on both sides, we basically get n cubed minus n squared plus 2n is greater than or equal to 10 cubed. So, we know that if we plug in n is equal to 10 cubed, we get 10 cubed minus, or n is equal to 10, we get 10 cubed minus 10 squared plus 20 is greater than or equal to 10 cubed. Oh, sorry, 100 cubed, sorry, that's trolling, okay. And clearly this is not true because this is 100 cubed and like 100 squared is greater than 200, so like this side is less than 100 cubed. But if we plug in 101 cubed, and then this will be 202, we basically get that we can factor this out, 100 squared times 101 minus 1 plus 202, and basically this clearly is bigger than 10 cubed, and then you're adding a positive number, so this works. So n equals 100 didn't work, n equals 101 did work, so our answer is simply 101. Very epic. N is equal to 101. Okay, epic. Let us move on to problem 11, or 10. I know, 9. I know how to count. This one was kind of bad. I'm not going to go through the whole thing because it's literally just listing out the possibilities. There was a way to do it with pi, but honestly, thinking about that during the test, it doesn't make any sense to me. So basically what I did is I wrote out A, B, C, D, E, F. A is attached to B, C, D, E, and F. And basically if you want to find seating arrangements that work, you can't attach A to B because they're already connected. So you can only connect people who are not directly connected already. And then you basically just go around listing it. So we start with A as the first one, and it could be to the C, and then C could go to E or F, so you go E, and then you just do all the casework from there. This diagram just makes it easier to list them out, but you're just going to have to go through all of them. There's really not that many. And basically you only had to do it for A, B, and C, and then you can multiply by 2, because these ones are basically the same as these ones. Dude, I'm so triggered at this problem. I literally counted by hand all of the possibilities, and it got 46 for one half, and I multiplied by 2 and got 92, but no, the answer is literally just 90. God dang it. Just make sure you look through all of your things that you listed and make sure they're all correct, and then you're good. But this is a really boring problem, so I'm not gonna go over it. Dude, the one combo they had is so bad, so triggering. Anyway, so for this one, basically you just had to know that the sum of cubes is n times n plus 1 over 2 cubed. And then what you gotta do is you just gotta long divide this dude. So if you want to expand this out, you basically get that it is n to the 4th plus 2n cubed plus n squared over 4, of course. But let us long divide it first. N plus 5, and we could do n cubed plus 5n, n4, oh wait, what am I doing? Oh, okay. N cubed, so this becomes n to the 4th plus 5n cubed, this becomes negative 3n cubed plus n squared, then this becomes minus 3n squared, and I could do it out. So this is basically what you get after you long divide. And then if we want to put back our divide by 4 in, sorry, there's a square here, we basically get that it's 1/4, or we could say that it's n cubed plus minus 3n squared plus 16n minus 80 over 4 plus 100 over n plus 5. So the first thing you could probably notice is that if this part is divisible by 4, then this part over here is just the remainder mod n plus 5. So essentially we could say that 100 mod n plus 5 has to be 17. And the only case that is if n plus 5 is equal to 83, which means that n is equal to 78. And this works, right? Because then, this is for sure divisible by 8, because n is divisible by 2, this is divisible by 4, this is for sure divisible by 4, this is divisible by 4, so this whole thing is divisible by 4. So this here is a whole number, and then this right here is going to give you a remainder of 17. So this is one solution. Now the other solution is when this part is not a whole number, because then this is not the only remainder you have to worry about. You might get some remainders from this like fractional part. So the only time when this is not divisible by 4 is when n is 1 mod 4. Because if you do 3 mod 4, right, you get 27 minus 27 and then plus some multiples of 4 here. So that's divisible by 4. But if you do 1, then you get 1 minus 3 is negative 2 and then multiples of 4. So it's not divisible by 4. So we had to find an n mod 1 mod 4 that works. So basically you know immediately that this part doesn't contribute at all because this is guaranteed to be like integer. So basically you know that if this is 1 mod 4, this basically is going to be like 1/2. So we know that n is 1 mod 4, so n is odd. So this right here is going to be even. So basically adding or subtracting a half from it is going to add like 1/2 of n plus 5 to the remainder. So essentially you have that 100 plus like, let's say n plus 5 over 2, mod n plus 5 has to be equal to 17. So basically we just want to solve this right here. You could like move this over here, you get 83 is equal to n plus 5 over 2. You multiply by that, you get n plus 5 is equal to 166, and that means that n is equal to 161. And we can check it, right? Because if we plug this in here, we get that this right here is going to be 83, so you get 183, and if we mod that by 166, you get 17. So very cool, we did it. We found 2 things. And you can prove that nothing else works, but like, that's kind of boring. On the actual test, it's not really that important, and if you could just like try like increasing n a little bit more, and you can see that it's just never going to work again. You can also just like notice that as you make n bigger, this is just going to keep getting smaller, so you're never going to get back to 17. Alright, we did it. We went through over 1 through 10. I hope it was helpful. That's basically how I did it on the test. I haven't looked at the official solutions yet, but hopefully this is helpful in like how you should approach problems. I don't know. I did spend so much time on 11. I'm kind of triggered at that one. I still got it wrong because I made a stupid mistake. I'll probably get redemption on that at some point, hopefully, and I'll show it to you guys, hopefully. Alright, thank you guys for watching again. As always, if you enjoyed the video, leave a like and subscribe for more. Thank you guys for watching a 3rd time, and see you guys next time.